Okay, so you guys got a little bit further than the afternoon section, so the initial slides are going to be review. So when we first talked about chapter 12 last Thursday, we looked briefly at chemical bonding and what makes up that bond. So what's our conclusion? What's going to make the bond between these two nitrogen atoms? What's the first thing that's going to interact between any atoms? The valence electrons. So if we're going to try and come up with a theory to explain the individual bonding, that theory is really going to revolve around the valence electrons. So what we're looking at is the sharing of electrons between these two atoms. Okay, so that's really what's making up our bond. The next big question that we could then address would be, well, are all bonds going to be the same? Okay, well, would we predict them to be the same? Probably not. Why not? The atoms are different. If the atoms are different, the electrons around them are different. They're going to have different energies, which means when they go in to make the bond, we're putting electrons in at different energies. We're going to get different results, okay, or different properties coming out of those individual bonds. Okay? If we didn't get different bonds, it's going to be a bit odd or boring world to live in because then everything would react the same. Okay? So we're definitely going to get those different properties. We've got the different types of bonds. We're going to add to this as we kind of continue to talk about it. We've got our two primary categories that we talked about within nomenclature. So your ionic bonds, which are a metal and a nonmetal, most typically. What's the one exception? We can get an ionic bond. All of our ionic bonds will involve some kind of nonmetal, guaranteed. It's always going to happen. Does it always have to be a metal? It doesn't always have to be a metal. What's the one exception? What was that? Nope. Carbon is a nonmetal. That's nonmetal. We're looking at a covalent bond. Hydrogen's still a nonmetal. The phases don't matter. Transition metal is still a metal and a nonmetal. No. It's at the top of that polyatomic ion chart that pretty much everybody has not seen it because it's such a small little one line on the top of the polyatomic ion chart that everybody just tends to ignore it. It says it's part of the title. Ammonium. The ammonium polyatomic ion is the one nonmetal cation that you would need to be worried about. Everything else is going to classify under that metal and nonmetal category. Or you're shifting into a different type of bond, say a covalent bond. Okay? So just be aware you do have that one floating exception. If you go back to the chapter 6 nomenclature, I think I didn't even star ammonium. Okay? And intentionally, pseudo-intentionally. I probably should have because it is the one exception and it does show up fairly often. Okay? So I just want you to be aware of that exception. It's not one that I'm expecting you to memorize at this point. Okay? When we move into covalent bonds, what are we bonding there? We'll take two nonmetals. Okay? Any two nonmetals and we're going to put them together. We can put multiple of each type of nonmetal together, so we can do something like water, where we have two hydrogens and one oxygen. Okay, but it's still two types of elements. So that's what we're concerned about with our covalent bonds. Are there other options? Can we bond more than just two different types of elements and make covalent bonds between them? Absolutely. It's what you would do in organic chemistry, okay, or pretty much any further chemistry down the road. The reason we don't address that now is they build up their own nomenclature system, their own separate rules, and we just don't want to open that can of worms yet. So at this point, you should be pretty happy that you're just dealing with two nonmetals, relatively simple structures, which will make the electron dot formulas a lot easier to process as well. Okay? And then are all nonmetal covalent bonds the same? Actually, even before we get into that, are there more than just these two bonds, ionic and covalent? Yeah, what's one category that might stand out as a possible option?
Metal and metal.
Metal and metal. You're looking at a metallic bond. Okay, it's the one that we're not going to address this semester. Okay, there's another option. We can look at kind of the gray area in between ionic bonds and covalent bonds. Okay, ionic bonds are ionic. What does ion mean? Charge. Okay, so when we put those two elements together, they completely swap electrons, and we get one extremely positive and one extremely negative ion in it. In a covalent bond, that can be subcategorized into two different positions. We can get a nonpolar covalent bond, which is typically how I would reference a covalent bond, and then a polar covalent bond. The covalent or the nonpolar covalent gets complete 100% equal sharing of electrons, so no charges show up on either end. A polar covalent bond, on the other hand, has some partial charge building. One of those elements is more electronegative than the other and starts to draw electron density away. Not enough to make it ionic, however. Okay, and we will look at those rules. That's where we're getting into this non-metal covalent bonds the same. Okay, we just said we get polar covalent bonds as well. Does it make sense to have a different type of bond? Well, if we take a look at hydrogen being bound to different elements, hydrogen bound to oxygen, hydrogen bound to chloride, okay, do we get a different type of bond in that case? Well, to consider that, do we get different chemistry? Okay. This is something that if you continue to take classes from me, particularly in organic chemistry, I like to determine something known as the face test, though it's not so politically correct. What do I mean by the face test? If we splash both of those in your face, are you going to be equally pissed off? No. Okay. You have a substantial difference between those two options. One is hydrochloric acid, not particularly pleasant, and the other one's water. You probably do that every morning or evening, depending on your schedule. Okay? So we get very drastically different chemistries with ultimately one of those atoms being exactly the same. That different chemistry means the bond characteristics, the bond nature, must also be different. Okay? Ionic bonds, I would classify them as kind of the 2-year-old, presumably, so I've been told, of bonding, because they just don't share electrons. Okay? So what we're doing is taking a metal near the nonmetal. The metal has very low electronegativity, meaning it doesn't want its electrons, so it gives it up rather quickly. And the nonmetal has very high electronegativity, so it completely takes the metal's electron. Okay, so we see a complete swap in the electron configurations. The result is that your metal will become a cation, which is just the fancy way of saying a positive charge. Our nonmetal will become the anion, which is a fancy way of saying the negative charge. Okay. And when we go through to put together our formulas, which species do we put in front always? The metal, or if we're going to broaden our terms a little bit, because remember we could have used ammonium. Ammonium isn't a metal. What term always goes in front? Cation, then anion. Okay, if we want to expand our horizons a little bit. In general, due to the regularity of charges, because we got this positive-negative issue with putting these together, you end up with very large, very organized structures. So what they've got shown there may look like just a bunch of spheres, but that's a very good representation of sodium chloride. We take an individual molecule of sodium, or formula unit of sodium chloride. So one of those is our sodium and one of them is the chloride. And we arrange other molecules very, very specifically around it to kind of balance out those charges. Because we're trying to balance out those charges, we tend to see very strong interactions between them, which means the melting points for your ionic compounds tends to go through the roof. Okay? What was the last time you saw liquid salt? There's a very good reason you haven't seen liquid salt, and that's because of these strong interactions between the individual molecules, if you will, or the formula units within sodium chloride. Okay? We're trying to neutralize those charges. Of course, we've looked at radii, we've looked at electronegativity. No space to walk over there. So now what we can do is look at ionic radii. So what happens to the radius of the element as we go through and change its electron configuration? Okay, so in this case, we've looked at both sodium, or we got the sodium element up there, and the chlorine atom up there in their standard states. If we're going to put them into a salt, the sodium ion, or the sodium metal, is going to lose one electron. Why does it lose only one? A couple answers I'll accept. First one would be it's in the first group, okay, which is the strict memorization way. What's the other way? That's still memorization. Sodium is trying to look like a noble gas. So we'll look at our closest options for our noble gas. We've got argon and neon. Which is easier for sodium to look like? Neon. How does it do that? It loses one electron. If it loses a negative charge, that's minus a minus one, that gives us a positive. Okay? What would happen to the size of our atom? Okay, so we removed electrons, so it should get substantially smaller. What does our electron configuration look like? So what is sodium ion? I was going to use the fancy word, but now I can't remember it. Let's see if you guys can predict it. Not taupe, electronic. Sorry, I just happen to remember it. Isoelectronic. What is it isoelectronic with? Iso meant same, electronic is referring to the electrons. What element is sodium ion isoelectronic with? Neon. It has the same number of electrons as neon. Okay, what determines the size of our individual element? Protons, neutrons, or electrons? Or all of them? Electrons. Electrons are our primary contributor to size. So if we go through and compare sodium versus neon, which one has more electrons? Sodium, I didn't say sodium ion. Sodium has more electrons, so we would expect it to be bigger than neon. Sodium ion now has the same electrons as neon. What happens to the size of our sodium ion? It gets much smaller. Would we predict it to be the same size as neon? Okay, it should be a little bit smaller. Why? We lost an electron, but we still have the same number of protons. So our positive charge is stronger in our nucleus. We would expect the size of sodium ion to be a little bit smaller. Let's go ahead and just do the mathematics on this. Smaller than neon. Okay, and that's because sodium ion has more positive charge to hold the same number of electrons. The electrons get pulled a little bit tighter. Okay. What happens to our chloride? Okay, so what's happening is we're now going to add an electron to it. Why does it add an electron? It's in group 7, which means, or that's not group 7, group 17, non-metal. We could have it memorized that everything in that column has -1 charge. Why do they all have a -1 charge? Just like our metal, it's trying to look like our noble gas. What noble gas is closest? Argon. How does chloride or chlorine look like argon? It gains an electron, so it's plus a -1. What's your official charge? -1. So it becomes isoelectronic with argon. What is that going to do for its size? Right? Within a row, what did we say happens to size? It gets smaller with our standard radii when we go left to right. Okay, why does it get smaller? All of our electrons are going into the same energy level, so we don't see any size difference there, but what's different about our nucleus? We get more protons in our nucleus. So as we go left to right, we do expect the size to shrink a little bit. Would we expect chloride to be smaller than argon in this case?
No.
Okay, the electron may be going into the same energy level, but does it have more protons to hold it? No. So what's the end result? It's going to get bigger. We are adding that extra electron, and there's nothing there to hold it tighter. So our size gets bigger. We would expect our chloride ion to be bigger than argon. Okay? Our end result is we could now look at the pictures and we could look at those radii. What is this going to tell us with our trends? As we go left to right in the periodic table, what's going to happen to our ionic radius? So the ionic radii now. It gets bigger. We shift from sodium, and we have to take into account now that when we're looking at our ionic radii, we're looking at their standard state charges. So the metals will always be positive. Our nonmetals will always come out as negative. That's going to have to contribute to our ionic radii definition. So as we shift left to right, thankfully we picked a nice example here. Sodium is in what energy level? Also known as what period? Also known as what row? Our third row down. Where's chlorine? Same energy level. What happens as we move from left to right to our ionic radius? It increases. What happens as we go down a column? Would we expect it to also change? Should it be the opposite of our atomic radius? Compare our sodium ion, we said was what size? Come on, right. There we go. We said sodium ion was what, bigger or smaller than neon? It was smaller than neon. Let's pick something like potassium, one row underneath. Potassium ion. What's it going to be isoelectronic with? Argon. So we'll compare it to argon. Should it be bigger or smaller than argon? Okay, a little bit smaller than it. Which element is bigger, neon or argon? Argon is bigger. Within a column, it still gets bigger as we go through our ions for our metals. Okay, because we're putting more electrons in. Why is this going to be confusing? Because guaranteed, what did you start to do? You said, oh, it's just the opposite of whatever the other one was, so I'm just going to memorize it's just the opposite. You can't do that. You have to understand what's happening with each of those conformations, which is what we just went through and discussed. Okay? So evaluate those electron configurations, what they're isoelectronic with, and then do your comparisons. Okay? It will help you go through and process and find these differences or these relationships. Okay? Questions? I know, Lindsay, you had one.
For some reason, I'm still confused why
Okay.
sodium is smaller than neon.
Okay, electron configuration for sodium. Sodium ion. Oh, I'm going to regret doing this. 1s, 2, 2s, 2, 2p, 6, 3s, 1, right? What happens to our sodium ion when we make it an ion? What happens to the electron configuration? So this was for our sodium atom. What happens if we become sodium ion? What's our electron configuration? The easy answer would be to start with 1s, 2, 2s, 2, 2p6. Do we have a 3s electron? No. So if we look at our electron counts, what contributes to our size? The number of electrons, right? What happens when we compare sodium to sodium ion? Sodium has one more electron than sodium ion. Which one should be bigger? sodium because it has more electrons. Does that clarify that? Okay. There's other smaller effects, and that's why we went through and compared it back to neon. It has the isoelectronic to neon, because neon looks the same as far as its electron configuration goes. Okay. So you should be able to tell me that sodium is larger than sodium ion. Everybody should tell me that. The challenge question would then be, what's the relationship between sodium ion and neon? That one requires an extra little bit of thought that we can't really put into play by looking at the electron configurations. We have to evaluate what else is different between the sodium and the neon, and what did we decide that was? The number of protons in the nucleus. Okay, well, our electrons go in closest to the nucleus first. Why? To balance out our charges. If we put in more positive charge, where's our electrons in the last electron in sodium ion going to be in comparison to the last electron in neon? Well, sodium has a little bit more positive charge, so that last electron is going to go a little bit closer because there's more of a positive charge in the sodium ion. Okay. Much more challenging question in that regard because you have to think about it. You can't draw electron configurations. Okay. Other questions with that?
So sodium ion equal neon,
Electron configuration, yes.
but then that equal and that is smaller.
So this is what I said. The size is not just the electron configuration. You have to evaluate the nucleus as well. We've talked about it now twice. If you want to ask more about it, we can talk about it after class. But I'm going to move on now from that topic. What happens when we move into covalent bonds? I don't have a child analogy in this case. Maybe kindergartners share better. I don't know. Okay. We're looking at sharing of electrons between the atoms. Okay, well, what's going to determine the sharing of electrons? Okay, what property of any element is going to tell us something about how well it shares electrons with another element? Not so much the charge. The charge gives us some hints to it, but there's another more important aspect. Particularly if we take a look at nitrogen and nitrogen. The bond between nitrogen and nitrogen, so we got up here, what's the charge on each of those nitrogen elements? If we said each nitrogen was -3, what's the overall charge on nitrogen gas? -6. What is the charge on nitrogen gas? 0. What is the charge on each of the nitrogens in a covalent bond? No charge. We cannot use charge to determine what's happening with our covalent bonds, which is why when we go through and do the nomenclature for it, we change the nomenclature system. When we look at our binary covalent compounds, we don't name them the same way as we name our ionic compounds. And that's because there isn't this unequal sharing of electrons. It is equal, which means we cannot go back to charge because they're sharing electrons. Okay? So if they're going to go through and share electrons evenly, we have to come up with a new definition. Okay? And when it comes up with new definitions, that means we have new rules for nomenclature, which is why when we define each of our nomenclature systems within that, we don't use our Roman numerals anymore. We don't have to specify charges. We don't balance charges to figure out the numbers of each element in there. We have to use the name to give us that information. So if we jumped to, say, H2O, what is the IUPAC name for H2O? Well, we've got hydrogen, and we have oxygen. In our conversion, our second element gets the "ide" ending. But since we don't have charges, we have to specify our amounts by saying dihydrogen. And allegedly, according to IUPAC, and I'm not sure I believe this from your textbook, but it's what it's got, the second element is technically always supposed to have our Greek prefix. So if there's only one, we have to add in mono. It's a bit redundant to do double O. So you can get dihydrogen monoxide. Okay? We changed the nomenclature system. Why did we change it? Because we can't rely on the charges to determine how much of each of those elements are present. Okay? This is also going to adjust how we look at radii. When we looked at our ionic radii, we had ions to compare. When we look at a covalent bond, are we changing the electron configurations? Sorry, that's my bad. No. They're equally sharing electrons. So if hydrogen comes in with an electron, it still has that electron, kind of, sort of, when it bonds to chlorine. Okay? And chlorine still has all of its electrons. So when we look at the radii, the effective radii of each of those does not change. But when we make it a compound, now what happens to the distance between those atoms? Okay, in an ionic compound, that distance is equal to the radii of one atom and the radii of the other. In a covalent compound, because they're equally sharing electrons, those electron clouds must overlap with each other. If they overlap, what happens to the distance between the atoms? It gets a little bit smaller. So when we look at the radii for HCl, so if we take a hydrogen atom and a chlorine atom and we put them together, we make the compound HCl. And you go through and take a look at the bond length. The bond length in the compound HCl is a little bit shorter than that if we just look at the radii. And that's because we're getting a different bond. We're sharing electrons between these two atoms. That sharing of electrons necessarily is going to bring those atoms a little bit closer. Okay? Do I expect you to be able to predict the bond length for any molecule? No is a good answer. Why? How would you be able to get the bond length? What information do you need to know? You'd need to know the radius of your individual atoms. All I could probably ask would be, in a multiple choice test, which of the following is a possible bond length for the molecule HCl? And I would give you the radii of a hydrogen atom and a chloride atom. And let's see if we can do a multiple choice here. Let's say, well, first off, let's give you the answer. 1.27, let's make that B this time. C as an answer would be 0.136. Anyone want to call me out on not using units? Let's give A being, oh, I don't know, let's make it fun. Let's call it, ooh, let's be really tricky, 1.27 angstroms. That's obnoxious, isn't it? Exact same number, but different units. Because angstroms confuses people. Let's change that. Let's make that a little more exciting. Where'd my red go? There it is. Let's call that meters. Okay. And then let's throw in, let's make E goats. Always go back to the goats. We have to put that on the test yet. And then let's try 0.0236 nanometers. Okay, within those options, it's a covalent bond. What does that tell you about the bond length? Okay, with our ionic bond rules, it's equal to the radii summed. Okay, so that could be C as a possible answer, because that is the sum of them. Could it possibly be goats? No. All right, I'll have to write a question where goats is the answer. Okay. Could it possibly be 0.236 units or nanometers? No, that's actually saying when we made the bond, we put the atoms further away from each other than they naturally are. Right? To do that, we're really saying that the atoms just aren't interacting with each other. So it can't possibly be that one. We could then be really, really careful and say, oh, shoot, he put in meters, different unit. That can't be right. Which now leaves us between B and C. How would you decide between those two answers? Well, you'd have to think back to this lecture or the textbook where it said, what happens to the radius or our bond distance in a covalent compound? Make it smaller. So 0.136 was just the addition of those two, which means it's got to be the one smaller. Okay? So it is still possible to ask it, but I have to give you a decent amount of information. I'd give you the radii of your atoms. Okay? And then after that, really there's only 2 reasonable answers. The rest should be tossed out. Questions about that? Okay. Bond energy. So what's happening when we make a bond? Okay, any ideas? What do you think happens to the energy when we make a bond? Should it go higher or lower? What do atoms want to transition to? Highest energy or lowest energy? Lowest energy. So if we're going to make a bond, what would we predict to be the energy of our resulting bond? Should be lower. So let's put in some numbers. Let's say the energy of our bond, our new molecule is 1, and the energy that we started it with was 100. Okay, why do this? Well, we want to look at the energy change. To calculate a change, what do? No, that's a per. A change is always a difference. And when we calculate our differences, it is always our final minus our initial. What was our final energy? 1. We made the bond. That was our end result. Minus our initial. What's our result? Negative 99 AMUs on the wall. AMUs is a bad unit. That's mass. Let's do joules. Okay. What does that minus sign mean? That's trickier. A minus sign means a loss. So in the course of doing this reaction, we lost energy. That energy has to be accounted for somewhere. Remember, we can't create or destroy matter. Where do we put our 99 joules of energy? Should that be a reactant or a product? What happens if it's a reactant? What's the energy on my reactant side now? 100 and, whoops, that's not a 9. 199 is my initial. So now I do 1 minus 199. That's not really a good number. That's saying we lost even more energy. Remember, in the course of a reaction, conservation of energy, the energy must come out to be 0, which means if we lose energy, really what we're saying is that our energy was a product. Okay? Now what happens when we do our final and our initial energies? Well, our final energy was was 1 plus the 99 joules minus our starting, and what do we get? 0. What does that mean overall? To make a bond, we lose energy. Kind of cool. What happens if we do the reverse? What if we break a bond? We're going to have to add energy into it. So all we're doing is now swapping the direction of that arrow and saying it goes the other direction. To do that, we have to include that energy. That energy is now a reactant along with our nitrogen, our N2 molecule. Okay? So what we're looking at for every individual, or not necessarily every individual reaction, but when we take a look at atoms in their gas phase and we make a bond between them, that reaction releases energy. That energy is most typically released in what form? Heat. Hence we write heat. Okay? Or if we put our hand up to the reaction, what would we feel? It would get warm, or hot, or burn your hand. Okay? Depending on how much heat was released. If we looked at the reverse reaction, if we need to break that bond apart, please say they gave it to me. Oh, much later down the bottom. All we're going to do is now take the HCl as a molecule with the heat. When we put those two together, we can then break that bond and split those into separate atoms. Okay? So what we now have is something known as bond energy. So that's the absolute symbol of this. Okay? In our first case, to make that bond, our energy, whoops, come back here. Our change in energy had what sign? It was negative when we looked at the bonds. What happens if we look at the bonds for our reaction where we break the bond? What should our change in energy be? Positive. If you think back to the lab, when an energy or a reaction lost heat, okay, we could call it a loss of heat, but we also gave it another name. What was that other name? Exothermic. What does exothermic refer to? The sign on your energy term is negative. What happened when our reaction gained heat? It was endothermic. What does endothermic mean? The change in energy has a sign of positive. Okay? Those signs have a physical meaning behind them. It's not just mathematical wonder. Let's call it wonder. Okay? So the next question then becomes is what do we define as the bond energy? In both those cases, what's the magnitude? Let's say for the making of that bond, it was a loss of 99 joules of energy. For breaking the bond, how much energy do we have to put in? 99 joules of energy. What we put in has to be the same as that we would get out in both cases. So when we refer to the bond energy, now we've got to be careful. Because in one case, it's negative 99. In the other case, it's positive 99. If we're going to go through and do a calculation using that number, we need to make sure we know whether it's positive or negative. How do we decide that? Arbitrary. Someone came in and stamped and said, the bond energy is defined as, should have highlighted it, the energy required to break a bond. That is the definition of our bond energy. What should the sign be on all bond energies? Positive. Why? Look at our two reactions. The only one that actually, or reactions, the only one that breaks those two atoms away from each other is the second one. The energy in that case is positive. So your bond energies will always get reported as a positive value. Okay? I don't think we're going to trick you too much with the phrasing with some of these problems, but we'll see what happens. I don't think I saw anything weird, at least in the homework. When you move into further classes, you're going to have to be very careful that you know exactly what that definition is. Because if I tell you that the bond energy for HCl is 99 joules, but then the question I ask on the exam is how much energy does it take to make the bond, what's your answer? Negative 99. Because the bond energy referred to breaking it. If I want to make it, I have to change the sign. Okay? Signs are really, really important to watch out for. Make sure you know what they mean beyond just that it's positive and negative. Okay? Yes?
So when it's positive or negative, that's only when it's bonding, not just being charged. It can't just be charged
Negative?
by itself.
No.
Okay.
It's a change in energy that requires something having changed in the course. Okay? We don't look at the specific energy for an individual atom. We'll always look at the change.
But it's if there is an energy or a charge, it's when it's bonding to something or.
If it's a negative energy, what is it? Is it bonding or breaking bonds?
Well, that's what I mean.
Okay. When is it negative? It is only negative when what happened? When it made the bond. If we have a positive energy, what is that? When it's breaking the bond. It will always be that. Okay. And that just comes from the dynamics of those reactions. Does that answer your question? Other questions with our bond energies? Okay. Are all bonds the same? Well, maybe from this slide you can take a guess at it. No, okay. Let's move on from there. We've got our ionic and we've got our covalent bonds. Our ionic bond is defined by this weird symbol that I've got specified up there. Our ionic bond is the case when we have something greater than 1.7. What is that 1.7 referring to? That 1.7 is the difference in electronegativity. Difference in electronegativity between what? Between the atoms within that make up that bond. Okay? If that difference is greater than 1.7, we classify it as an ionic bond. So how do we figure out that sodium chloride is an ionic bond? We look up the electronegativity of sodium, we look up the electronegativity of chloride, and we subtract those two. Okay? If that number is bigger than 1.7, it is an ionic bond. Okay? That is the strict definition of ionic. Anybody see a problem with that? Maybe a slight panic going through your mind. What's the slight panic? That's a good thing to panic about. What if it comes out to exactly 1.7? And I'll address that in a slightly different fashion in a second. We can throw in a greater than or equal to. It's not that big of a deal to do that. I actually don't know exactly if it's greater than or equal to or if it's just greater than. What was that? Someone said something. Memorize. You would have to know the electronegativities of every single freaking atom so that you could go through and calculate the difference in electronegativity to tell you that it's an ionic bond. Do we have an easier definition? Metal and a nonmetal. Go through with all of your metal and nonmetal compounds. Look at their electronegativities. You're going to have to look at the binary ones. But if you go through and do that, what are you going to find? The difference between your metal and nonmetal electronegativity is greater than 1.7. It works. Okay? What happens when we get into our covalent bonds? You'll notice there's two categories here. Typically, I classify covalent as the nonpolar section of it. But for it to be a nonpolar covalent bond, what we're saying is that those atoms in that bond equally share their electrons. So it's super, super strict. When's the only case that we're going to get atoms equally sharing electrons? Not charges, not same family. How did we define this? It's based off of the electronegativity. If they have the same electronegativity, say hydrogen and hydrogen, we now have equal, 100% equal sharing of electrons. It's nonpolar. What do we mean by nonpolar? No charges. No positive, no negative. The complete opposite of an ionic bond. The problem with that definition, it is excessively narrow and it limits a lot of our potential chemistries, okay, or our predictive abilities. So the definition is broadened ever so slightly, and our nonpolar covalent bonds are typically classified as something with an electronegativity difference that is less than 0.5. Okay? Again, how would you decide it's a nonpolar covalent bond then? Know all of the electronegativities, do the subtraction to figure it out. Oof. I've never seen units on electronegativity. I don't know what to tell you with that. I'm going to take a stab and say that it's unitless. Okay. Yeah.
Can you say it must be no charges, that they're like they balance each other?
When we look at sodium and chloride, what does that bond do? Where do the electrons in that bond spend most of their time? With the chlorine atom. So all of those electrons go onto the sodium, and we better represent that structure as Na plus and Cl minus. Why do we call it an ionic charge? Because we see charges, period. It doesn't have to be that they're balanced necessarily. In this class, they will be balanced, but that's not a necessary requirement of it. Okay? When we get into the hydrogen, where do the electrons spend most of their time between the hydrogen atoms? Equally between both. If they spend their time equally, we can't build a charge. We can't get a positive and negative. So it's nonpolar. We don't have the polarity of a positive and negative system. Okay? What happens with that extra definition? Polar covalent. Okay? This is kind of an interesting category. So one of the things that, or at least the way we've sort of presented it so far, is that our bonds are ionic, purely, or they are covalent, purely. As soon as we go through and add this definition of our difference in electronegativity, now we have this big gray area between 0.5 and 1.7. Do you think it's possible to build an atom or build a bond that has an electronegativity difference in that range? Yeah. And that's where this strict defining these things as individual bonds becomes a problem. Right? Because it's not a strict line. Okay? If you take a look at the rainbow spectrum, can you tell me exactly where the red color stops and the orange color starts? No. If you took a section of red and a section of orange, you could say, yeah, they're different. Okay? But that exact line on where it stops, we can't see. Same thing is happening with our bonds. We aren't ionic, polar covalent, and nonpolar covalent. We are looking at a spectrum, okay? Starting from completely sharing electrons with our covalent bonds and moving up to completely not sharing electrons with our ionic. And we have a massive gradient in between it. Okay? With the rainbow spectrum, do we still define red? Can we tell a difference between red and blue? Yeah. Which is why we come up and say one's red and one's blue. Okay? So what we're doing with our bonds is the same idea. A covalent bond is not an ionic bond, very clearly. Okay? Our ionic bond is, say, red, and our covalent bond is purple. We can see that difference relatively clearly. We want to delineate those possibilities. Our polar covalent bonds now fill the gap in between. Okay? To officially classify each of these, you really have to know the electronegativities behind it. That's not something I expect you to do. There's a couple little secrets or shortcuts that we can pull on these. What was our shortcut for our ionic bond? Metal and nonmetal. What's our shortcut with our covalent bonds? Okay, we could do nonmetal and nonmetal. That would classify for both covalent types, both polar and nonpolar. So that definition at least tells us covalent, but it doesn't allow us to differentiate between these two. So both of these are nonmetal, nonmetal. Same electronegativity we could do, but to do that, you need to know the electronegativities. We said we don't want to memorize those. How else could we differentiate our nonpolar covalent from our polar covalent? It's easier than you think. What's that? The way they share electrons comes back to the electronegativity. So one is separating charges. We'll draw that out in a second. What's the example that we gave for a nonpolar covalent bond? Hydrogen bound to hydrogen. What's the difference in electronegativity there? 0. What if I did chlorine bound to chlorine? Or phosphorus bound to phosphorus? Same. What's one of our rules that we could come up with? Same bound to same. Same to same is a nonpolar covalent bond. Okay? The next little trick that we'll throw in there really just comes from organic chemistry. Carbon bound to hydrogen is classified as nonpolar covalent as well. So then what does polar covalent become? Everything else. Okay? Does this work perfectly? Absolutely not. Does it work 80% of the time?
Yes.
Yeah. Okay? If you move into organic chemistry, we'll simplify that polar covalent down a little bit more. The reason why I can't simplify it in this case is because there's a whole lot more elements that you guys have to deal with. In organic chemistry, remember, we only deal with 10, so we can simplify this a lot.
So carbon and hydrogen are not polar covalent?
Are not polar covalent. The difference in electronegativity between them is less than 0.5. That puts you in the non-polar covalent category. Okay? What does my next slide show? Yeah, I was afraid of that. So, Kylie, you asked something about what's going on with that polar, what's happening with polar. Okay, well, let's erase. Can I erase everything? Okay, well, sorry. Let's take a look at our hydrogen and our chlorine. I'm going to draw it a little bit bigger. Let me draw it smaller then? Oh, that was wrong color. Close enough. I drew over the top of it. Where do the electrons in that bond spend most of their time? Why with the chlorine? So officially, electronegativity. Can we come up with a hand-wavy argument? They're both nonmetals. I know, hydrogen's a weird one. I keep forgetting to talk about this. Hydrogen, you'll notice, is on the far left side of the periodic table because one of its chemistries happens to match with the plus charges. Okay? That's its most common ionic state. It can also be negatively charged, which means in some periodic tables, you'll see the hydrogen over group 1, and you'll also see it over group 17. Okay? Hydrogen is officially a nonmetal. Looking at our periodic tables that are in here, how do we know it's a nonmetal? It's red. What does red mean? It's a gas. Are any of our metals gases? No. Okay? So we're looking at two nonmetals, so we can't run with that. You guys were suggesting this option earlier. What's the electron or the charge on chlorine? Chloride. We put it into a bond. -1. What's the charge on hydrogen? +1. Why does hydrogen go to +1? So now its electronegativity is relatively low in comparison to the things we bond it with. Whereas the chlorine has an electronegativity that is relatively high. So the electronegativity can be sort of compared to your charges, not perfectly, but it works a little bit. Okay, why is that going to be helpful? Where do the electrons spend most of their time then? With the most electronegative or the least electronegative? The most, which means the chlorine takes those electrons a little bit more frequently than the hydrogen. Okay, so if we look at it as an average across time, the electrons spend most of their time with the chlorine, which means what charge does that chlorine start to build? It's gained electrons, so it is plus a -1, negative. Is it formally negative? Does it always have those electrons? No. So what we have to do is come up with some way to say, yeah, it's negatively charged, but it's not always negatively charged. So the notation we come up with is some of the times it's negative, and some of the times in German begins with the Greek letter delta. Guess I like making fun of the Germans. Okay? The delta symbol just means a difference. The difference over the average of this molecule says that that chlorine will be negative. If that chlorine becomes negative, what happens to the hydrogen? It becomes positive. But is it formally positive? No. Only some of the time it's positive. So we go back to our German Greek letter delta, and we get the delta positive hanging out over the hydrogen. Because they are equally sharing electrons. And are our electrons fixed in any one position? No, they can jump into different places within an orbital. Okay? So just like we have that bond, those electrons can spend some of their time closer to the chlorine or some of their time closer to the hydrogen. Which means, as kind of an average over the whole lifespan of the hydrogen chloride, most of the time the electrons spend their time with the chlorine. Chlorine starts to become more negative than the hydrogen.
But, like, this might be dumb, but we say, like, with the elements are constantly
Uh-huh.
So when they bond, is that what they're doing by sharing? They're
Yep.
trying to stay neutral?
They're trying to stay their neutrality, yeah. One other notation, and I can't remember if the textbook shows this one or not, is this arrow. What is the arrow showing the motion of? The electrons. Our electrons are moving towards the chlorine. What charge builds on the hydrogen? What is this little symbol over here look an awful lot like? R plus. So what we've done is put in these partial charges to explain something about the difference in those charges. Why would those be closer to the ionic bond in characteristics? Because they have these charges. They're starting to approximate an ionic bond. Are they exactly an ionic bond? No, why not? Because we've got that little delta symbol saying it's not formally positive, which is what it would be if we shifted into the ionic bond. Okay? So it's just another way to represent that overall molecule. Okay? How can I ask this on a test? More than likely, it will not be multiple choice. It'll be a short answer explanation. I should erase that.
Give us a question.
That's what I'm doing, working on it. I've got to erase some space. I'd give you this and say, provide the partial charges. So partial is that delta symbol. What are the partial charges in this structure? So -2 assumes we have formal charge. So it's sometimes minus and it's sometimes positive. We can't ever push beyond the 1, because once we've cleared that 1 threshold, we've now become formally charged. Okay? So one of those is going to be typically minus charge. Which one is that? Our oxygen. One of those then is going to necessarily become, which will be the hydrogen. So you would just draw on those symbols. That's it. So we're not it's not hydroxide. How do we know this is not hydroxide? There's one huge clue that I left off of it intentionally. Hydroxide is negatively 1 charged. Did I specify a formal charge on this? No. All we're looking at here is the bond between oxygen and hydrogen, and that is it. Do not add your own information on top of it.
So if you have the same combination of elements.
As a question, yes. Yes. Because I don't want you evaluating the other parts of it. I could go through just as easily. I mean, if you really want to get into it.
You want to play that game?
What is the partial charge on the oxygen and the hydrogen in that bond?
Negative.
Okay. There's a whole bunch of extra junk there, even though the question's the same. Why add all that extra junk? I'm going to call you out on this, sorry. Because Thor asked for it. Okay. Why did I not include it in the first example? Because all it's going to do is confuse you and not get to the question that I wanted to ask, which is, where's the electron density in that bond? That's it. Okay. So you can make it more difficult. We'll stick with the simple comparisons. Okay. When are we done? 40? Okay. I definitely wanted more time on this. So we'll definitely do simple examples of these on a test. These are going to be short answer questions on the test. I cannot ask easy multiple choice questions on these. Okay? So Lewis went through with all of this information, and he wanted to start to explain how these atoms could bond. Okay? So he went through and looked at simple examples, which is where your test is largely going to center around. Simple examples of how the valence electrons on one atom interact with the valence electrons on another atom. Okay? So he went through and said, let's pick the simplest one. Let's pick hydrogen and hydrogen. Okay? So what's our electron configuration for a hydrogen atom? 1s1, and an electron configuration on our other hydrogen atom. What was it? Still 1s1. Okay? It still has just one electron. It's a hydrogen atom, period. And what he went through and did is brought these atoms close to each other, and hey, we formed a bond. Okay? Why would we expect to form a bond in that case? How many electrons fit in an s orbital? 2. How many electrons am I bringing into this? 1 from each atom. If I bring them together, 2. And I've now filled my orbital. It actually makes sense to bring these 2 electrons near each other, so we fill our 1s orbital, and we now have a bond. They have to share those electrons between them.
Wait, 1 is 2.
Okay. We didn't talk about charge at all here, and there's no charge. What's the charge on a hydrogen atom? 0. There is no charge. What's the charge on our other hydrogen atom? 0. When we bring 2 0 things near each other, what's the overall charge? Still 0. Okay? So that one kind of makes sense. But what happens when we jump up to, say, fluorine? Is it really just 1s1 anymore? 1s2, 2s2, 2p5. Okay, so it got a lot more complex. Jump up to CH4. Now it's not just 2 atoms. Now I got 4 atoms I've got to explain. Okay, so very quickly our simple comparisons, oh, we just fill the orbital, starts to fall apart, and we have to come up with a new theory. What he ended up noting was that if we go through and look at these configurations, what happens if I add an extra electron to fluorine's electron configuration? I fill it, right? Okay, I fill what energy level? What energy level? Energy level 2. I didn't ask what orbital type. Okay, how many electrons fit into that second energy level? Maximum into the second energy level, we get 8 electrons. All of the structures that he was looking at were relatively small and simple. Okay? So he went through and saw this patterning of 8 with a lot of these compounds. If we move to CH4, our CH4 compound, again, our carbon is missing 4 electrons in that outer energy level. 4 hydrogens could come in and fill those gaps. So he looked at patterns of 8 and said, okay, atoms are probably going to be very similar to larger structures. What's a structure, a larger structure, that we could all visualize that has 8 points? 8 points. Cubes. Why is this important? Well, he went through and said, okay, well, I'm going to look at, say, HF, and what's happening is I've got my hydrogen atom nucleus in the middle of this cube, the fluorine in the middle of that one. Hydrogen comes in with 1 electron, so we'll put that 1 electron at a cube intersection. How many electrons does fluorine bring in for its valence shell? 7. 1, 2, 3, 4, 5, 6, 7. Interesting. That one space on our fluorine is missing an electron. Well, what can happen? Let's mesh the face of this hydrogen with the face of that fluorine along that line. We've now formed a bond where we've shared the electrons between them. Okay? Big issue with this. How many of you are good at drawing cubes? How many of you want to become really good at drawing cubes? Or say for CH4, where now it's not just 2 cubes, we've got 5. Really want to start doing that? That theory becomes a bit tedious to draw these things out. So what we've done instead is convert it into 2 dimensions. In that 2-dimensional space, what we're going to end up doing is saying that our hydrogen comes in with its 1 electron. Our fluorine comes in with its 7 electrons. What shape have we generated now around the fluorine? Effectively a square. So what we've done is shrunk down Lewis's ridiculous cube theory into a reasonable 2-dimensional shape. What's special about this? We now have 2 electrons between 2 atoms. What happens when those 2 electrons get close enough to each other? They form a bond. So we now have a bond between these 2. That's an awful lot of dots to be showing in there. So let's simplify our drawing and call a bond or draw a bond a different way. How do we draw a bond? We convert those 2 dots into a single line. And we now have a Lewis structure for HF. If we go through and do this for, let's see, what's my next slide? Yeah, we can open that up. Do it for CH4. Okay, so our hydrogen comes in with how many electrons? 1s1. How many hydrogens do we bring in? 4, which means hydrogen brings in a total of how many electrons? 4. We have one carbon atom. Its electron configuration, 1s2, 2s2, 2p2. Of those, how many electrons do we consider? Why just 4? Only concerned about the valence electrons. Okay, so we can ignore anything or any of our core electrons. So how many electrons does carbon bring in? 4 electrons. When we go through to build the structure for CH4, what we're going to do is arrange these atoms in a very particular fashion, which we'll talk about here in a second. Why would I try and put those hydrogens as far away from each other as I can? What's that? That's a reasonable answer. What's another answer? Let's say we put the bonds on carbon. The protons are going to repel each other within the individual hydrogen. So they're going to try and bounce away from each other as best as possible. Another reason, this is a two-dimensional drawing. Would you really, really like it if I decided to put all the hydrogens right here?
No.
Okay. It looks ugly. Okay. We said we had 4 electrons from hydrogen, 4 electrons from carbon. Okay, so one method is to go through and put in our electrons for each species. Why am I putting the electrons all facing the carbon in this case? Because we're trying to explain bonds. Where do the bonds form? Between our atoms. Carbon came in with 4 electrons. Why did I space them evenly around the carbon instead of grouping them all together in one spot? Slightly different feature here. When we put electrons into orbitals, where do we put our electrons first? Lowest energy. Where do we put them next? Next energy level, up, right? Then we put them into the p orbital. So in our p orbital, our first electron goes into the p. Where does the second electron go? That same p orbital goes into a new type. Why? We want to avoid that pairing of electrons. So when we go through to evaluate our carbon and put electrons in, we're going to put our electrons as far away from each other first before we start pairing. Okay? Remember, we're still going based off of this cube idea. Our simplification was to make it a square. So we're going to look at the 4 sides around our carbon. We can now evaluate any place that we have 2 electrons between atoms. What do we make? What do we have now drawn? The electron dot structure, or the Lewis structure, for methane, CH4. Okay. To go through and do this, of course, I picked the easy examples to start. What we have to do is come up with a sequence of rules. Okay? I'm going to kind of leave you to read through the rules a little bit because I want to cover a couple more examples. We'll talk about these in general. Rule number 1, get all of the valence electrons totaled. You need to know exactly how many electrons need to go into your structure. Okay? Choose a central atom. That central atom needs to act as a bridge. What does a bridge do? Connects 2 places. Okay? If it's connecting 2 things, how many bonds do you think it has at a minimum? 2. Can hydrogen ever act as a bridge? No. Okay? So in general, our central atom is usually the least electronegative, our exception really being hydrogen, or anything that can't bridge. We're going to add electrons in pairs. So now we're going to tweak the definition from what we just did. We'll add them in pairs to the most electronegative element first. How many electrons do we want to put around our individual or our most electronegative element? 8. Why 8? There were 8 points on the cube. That satisfies our octet to get us to our noble gases. If we still have electrons, you can then start putting them around other elements until they satisfy their octet. There's some weird steps within that. What do I mean by their octet? How many electrons should be around a hydrogen? 2. Why only 2? It's the 1s orbital. It has no p orbitals. It cannot put electrons up to 8 electrons around the oxygen. Or, sorry, around the hydrogen. Okay? Anywhere that you have pairs of electrons between atoms, you can convert it into a line, so you can erase your dots into lines. The next 2 rules we'll worry about after exam 2. Okay? So those will be not on the exam. Not exam 2. Okay? So let's look at a couple more examples. We just did CH4. So let's do, we're going to run a bit tight here, but we'll do the NH4 plus and the OH minus. Okay? So NH4 plus, we need to total the electrons that go into our structure. How many electrons does nitrogen bring in? Since we're getting a bunch of different numbers, nitrogen, 1s2, 2s2, 2p, 3. What are our valence electrons? Nitrogen brings in 5 valence electrons. How many electrons does our hydrogen bring in? 1 electron each. How many hydrogens do we have? Sorry, let me make that a little bit nicer. 4 times 1. What's that plus charge mean? We lost an electron. Which means when we go through the total, what do we have to make sure we account for? That we lost that electron. This gives us what for a total? 8 electrons. So this was our nitrogen, our hydrogens, and our charge. 8 electrons need to go into our structure. Rule number 2, pick your central atom. Typically it's the least electronegative, but it must be able to bridge. Can hydrogen bridge? Nope. So our central atom needs to be nitrogen. We can then scatter our hydrogens around it. Okay. We're then going to start to put in our electrons to the most electronegative element first. Which is our most electronegative element? Nitrogen. So 1, 2, 3, 4, 5, 6, 7, 8. I have now put in all of my electrons. Okay? If all of the electrons are in, I can't continue to add more electrons. Why? I don't have any. Okay? That's why we totaled the electrons to begin with. Now what we can do is convert any pair into a line to represent a bond. This is why students don't like this method, but it works better than what the textbook says. We erase, make a line. Erase, make a line. Erase, make a line. Erase, make a line. Check our octets. How many electrons are around the nitrogen? 8. We'll count each of those bonds as 2 electrons because how did we make it a line? We needed 2 electrons. So there's 8 electrons around our nitrogen. How many electrons around each hydrogen? The bond, 2 electrons. We've satisfied hydrogen's octet. It only wants 2 electrons. We now have a potential for the Lewis structure. We know that that structure is overall what charge? Plus 1. How do we know it was plus 1? Because our formula said it was plus 1. It takes a little bit of practice. I will tell you the lab next week is all doing this. That is the end of lecture. If you got questions,